Okay, good morning. So I'm a PhD student from the University of Wuppertal. It's near Cologne in Germany. And I talk today about the influence of input parameters on the fire simulation. After a short introduction, I will present some laboratory experiments, especially the TGA. So you already heard something of it. And after that, I will present some CFD simulation in the laboratory scale and also in the scaling, and I will scaling up it in real dimension. So after all, I will conclude it. I will shortly conclude the presentation after a short conclusion. So what is my motivation? Every user is asking himself, is my simulation realistic? So the usual proceeding of modeling fire spreading, at first the fire will be defined by the user. So for that, a lot of influences have to be determined. For example, the material properties, so you can find it in literature, or also you can do it with individual experiments. So of course, literature values are also a result of experiments. Furthermore, the assumption of the modeling do not necessarily meet the boundary condition of the specified user conditions. So because of that, the specific user conditions might only in part be in agreement with the model assumption. But today I will focus on the user-dependent influence parameters. So I'll take a look on the fire spreading modeling. The challenge of models fire spreading, like reproducing an experiment, is quite popular. So in this work, we at first done some laboratory experiments with the TGA, and with the results of it, we developed input parameters for FDS. These input parameters were implemented in FDS with respect to different experimental conditions. So you see here the simulation part. So I differ between laboratory scale, so it's the TGA or the cone calorimeter, and also the real scale dimension. So let us see the first step. In the presentation before, you heard a little bit of the TGA, so I shortly summarized. We take different samples which were heated by determining heating rate. So we're doing this heating process. We're recording the mass loss and the temperature of the sample, also the heat flux. And we vary the heating rate. So we done it with 5 Kelvin per minute and also with 60 Kelvin per minute. And we limited the oxygen concentration from 21% to 10%. So our samples we tested were a Lego brick. So it consists of ABS, a flexible foam, which consists of polyurethane, and also we tested PMMA, black PMMA, and particle board. So polyurethane was crushed, but it's the only one. While the other samples were tested in the initial configuration. So if you have a look on the results of the TGA, different process of decomposition and dependencies were figured out. So at first we see we have different residue for the thermoplast. For example, PMMA and ABS, the residues vanish. So we have only 0.1% PMMA residue and 1.5% for ABS. So, and on the other hand, charging materials like particle board and also polyurethane have a residue between 6 and 8% or 1%. So you see here, the two different residue of different heating rate. So one of it was tested with 5 Kelvin per minute and the other one with 60 Kelvin per minute. So furthermore, the physical conditions changed. So we have melting processes and also shading processes. And the oxygen concentration also influences the heating processes like the thermal initial. So for a better understanding, exemplarily, do you see here PMMA? On the left side, do you have the results of 60 Kelvin per minute, and on the right side for 5 Kelvin per minute. So the left y-axis presented the mass fraction, normalized mass fraction, so it's green plotted, and the right y-axis is the reaction rate, it's black plotted. So we have two samples of different suppliers. The same we see it here for 5 Kelvin per minute. We have two different suppliers, supplier A and supplier B. With 60 kelvins, the reaction starts at the same temperature. And we see also a difference in the maximum of the reaction rate. For 5 kelvins, the development of the plots are not so similar. So it's very simple. So with the increasing heating rate, the little reactions in this beginning vanished, and also the pyrolysis range, or in other words, the temperature range of the reaction increases with the higher heating rates. So for that, we see 5 kelvins, although it's the same material, we have different pyrolysis processes here. So we see here the influence of the oxygen concentration. So the dotted one plot is the oxygen, the test by 21 oxygen concentration, and the continuous line is plotted for the 10% concentration. So we also see here the reaction begins at the same temperature, but the reference rate is nearly a bit higher. Of course it's so, because we have a lot of more oxygen and the combustion works much better, and so the reaction rate is higher. In difference to the general described reaction of polyurethane, we have the third and fourth reaction. So it is an advice or a sign for intentional additives from the supplier. Do you see here a sketch of the 4 reactions? It doesn't matter which oxygen concentration we used. The 4 reactions, 1, 2, 3, 4, were also observed. So please keep in mind this little sketch here. So I will come back to it later. So if you have these results of the TGA, so we want to implement this data for the FDS simulation. So do you see here the normalized mass fraction for the particle board? of 5 Kelvin per minute. And here are the first and second derivation. That means, do you see the normalized mass loss rate? So between the maximum of the mass loss rate, we have one reaction, and the lower world, so you, for example, you can see it here, it's evaporation of water, so until 100 degrees. And between these maximum, you find the temperature, the reference temperature at the minimum. So the pyrolysis range is the range of the temperature at which the reaction exists. So you see here colored, black and red colored steps. So every colored is one reaction. With help of the temperature reference, so we can determine the reaction rate. And with all of these parameters, we get the Arrhenius parameters with the help of the implemented FDS pyrolysis model. So we simulated with the determined input parameters. So, and you can see here the dotted ones are the simulation, and the continuous line are the experiments. And here in this area, these reactions are simplified. Also, we can see it here for the 60 Kelvin per minute. So it means that it's not possible to reproduce exactly the plot of the reaction rate, but however the mass fraction fits very well. So interesting is here also, do we see particle board for 5 Kelvin per minute, 60 Kelvin? So I said it again, with a higher heating rate, the little reactions vanish. So, and also the process, the pyrolysis process is not finished yet. So we see it here, the mass fraction also is decreasing. So we take this simulation only to focus on the pyrolysis parameter. That's why we did some boundary consumption. So we doesn't take into account the combustion by reducing the oxygen concentration, and also the thermal influence or the thermal properties were neglected because the sample was very, very thin and the heat coefficient was very high to guarantee a homogeneous heating. So this model, based on the TGA example of the FDS user guide, and we take it for a guarantee that we get the right Arrhenius parameters to simulate it with the following simulation, like the cone experiment. For the cone experiment, we define the thermal deep. So the thermal properties are now necessary and has an influence of the simulation, like the density or the conductivity or the heat capacity. And we focus for this simulation on the mass flow rate and the heat release rate. So we're taking the determinant Arrhenius parameter and put it on in the cone simulation to compare it with real-done simulations, real-done experiments of the cone calorimeter. So you see the particle board. It's different from the typical method of ISO 5660 because we conducted without the frame. So we did it because in this way, the whole surface of the sample gets enough supply of oxygen, and the combustion begins all over the surface and the edges are not excluded. So we see here on the left side the experiments of the cone colorimeter by Arrhenius parameters with 60 Kelvin per minute, and here was 5 Kelvin per minute. So on the right axis you have the heat release rate, on the left the burning rate. So the continuous line are the experiments, and we have here the simulation. So you can see it doesn't fit really. So the tendency is the same like here, but it's shortly. And also we've seen it here for 5 Kelvin. So Arrhenius parameters, they're also not fitted. So independently of the Arrhenius parameter, I've added some material properties for the charging process. Otherwise, to simulate the cone colorimeter for particle board is not possible. So very simple, PMMA, you already seen it, but PMMA is very simple in this behavior of burning. It's burned continuously, and so we have the possibility to implement the Arrhenius parameter directly in the cone simulation. And this is the result of 60 Kelvin per minute, so it fits very well. This little difference should be no problem, because you can adapting the thermal properties. So here, maybe you can remember at the beginning, in the first lower temperature, we have little reactions. So these little reactions were also implemented for the simulation. Because of that, we have here a result which doesn't fit. So, but if we reduce these 3 reaction steps to 1 reaction step, we also get the same plot. So the difference is only for 60 Kelvin. The TGA experiments show us only one reaction. For 5 Kelvin, 3 reactions. So the user should know how the material works to define the real number of reaction which is necessary to simulate it, and also to difference between the and also to understand the differences. So we take the Arrhenius parameter, which we also take for the cone colorimeter, and implement it for virtual real scale dimension. So it's only an example. This share consists of particle board. We have also the Arrhenius parameter for 5 Kelvin and for 60 Kelvin. So the fire spreading is for the 60 Kelvin faster, and also the heat release rate is higher. So do you see here the top 500 kilowatts for the lower heating rate and 700 kilowatts for the higher heating rate. Another example is a polyurethane. So maybe you remember the sketch. So we have our four pyrolysis processes, and we reduce this 3 pyrolysis processes to 1. And we can see here that we have fire spreading, a very fast fire spreading, and a completely fire spreading for only 1 reaction, and for 2 and 3 reactions, we have a delayed fire spreading. So why could it happen? It's very simple. If you reduce the reaction numbers, you also reduce the heat of reaction, and the heat of reaction, the energy which doesn't get lost could be used for the combustion. So that's why for only one reaction, you have more energy for the combustion. So, totally, with all the simulation, all the experiment, it would be clear that the transfer of material properties to one scale to another scale is limited, and also that modeling the fire scenario by adjusting only one parameter could be ends in a worst case scenario and also in a Helmholtz scenario. So we see it with the sofa or also with the chair. For experiments, one change in configuration, like the oxygen concentration or also the heating leads to a complete change in fire behavior, could be, and also the Arrhenius parameter or the input parameters will change. So what's it for our conclusion? So the user have already determined the input parameters by his specific fire scenario because they are very sensitive, and the model procedure has to be clarified and very clarified, transparent, and documented. Also, the definition of material properties, especially in literature. So we also see that a classification maybe could help for the materials. So having simple burning behavior like PMMA or a melting process or a charging process. So we just had to implement some attentionally material properties or material layers. And also, independent of all these facts, the user needs a lot of experiments to show the right input parameters and to show the realistic input parameters for the FDS simulation. So I'm already finished now.
We have time for a couple questions here. So, Kevin, I'm going to ask you. I've never done pyrolysis. Is this the way we're heading in general now, to do a pyrolysis, that eventually you're hoping there will be data for the different materials, and we will then have those parameters that we use? Although I noticed you also commented you thought maybe she didn't have Fibric on the sofa?
Yeah, well, you'll notice the last two talks, basically PhD thesis. You know, this is typical like PhD thesis, and you probably worked on this for how long? How long did this work take you?
Not long.
What's not long?
Say 2 years, 3 years.
Like
4 months.
4 months.
4 months. Okay. So my goal is that you could take a chunk of this carpet, go to a testing lab, say run, you know, test A, B, and C, let's say TGA, DSC, MCC, and do this kind of analysis that she described and that the previous speaker described in a day or two. Otherwise, this isn't practical. Otherwise, you're going to end up either just taking material properties out of handbooks, out of the literature, or perhaps just doing a cone calorimeter experiment and then taking the heat release rate from the cone calorimeter and just sort of plugging it directly into FDS. So I think this is all good work and they're all heading in the right direction. My concern is the expense and the time. That I would like to see this streamlined to the point where it just becomes cookbook, and that you don't need a PhD student to do the analysis, that you run with standard equipment, ISO, ASTM, and so forth, and that the analysis method that they've shown here could just be done like scripted, literally a simple script, take the output from these apparatus and boil it down into the input parameters that we would need for FDS.
So do you have other questions?
Yeah,
So the question was, what do we need to get to that point? Is it a software question or is it a hardware question?
I think it's a business question. The testing labs, in order to buy this equipment and develop this expertise, have to have a payoff. And right now, I don't see the payoff. That is, I mean, what would compel, Southwest Research, Underwriters Laboratories, and the comparable laboratories in Europe to hire these kinds of people or, develop this kind of equipment? And would there be enough business to keep these apparatus running every day? We have these apparatus at NIST, and every time I ask the leader of the group who manages them to do some of this work for me, the apparatus is broken. I mean, if you don't keep this stuff working, like literally on a daily basis, it's broke. So, there's just, it doesn't seem to be right now a critical mass of work going on that would sustain this. And so that's my concern. I think that they have, the students and the professors who have done this over the last 20 years, I think they've more or less nailed down the technique. I think they know what they're doing. The question is, can we do it practically? Can you take a handful of samples to one of these labs and for, I don't know, $1,000 US in a few days, get back what you want? I mean, much like you can do that with a cone calorimeter. You can get cone calorimetry done at a testing lab for a couple $100 in a couple of days. This type of thing still seems to be taking far too long, and it seems to cost far too much.
Just had a question from one of our live viewers. On one of your slides, was 0.01 or 0.1 used for the 10% oxygen simulation? One of the slides said 0.21 versus 0.01. It said maybe one of the values used for your setting for oxygen percentage in the 10% oxygen. Maybe it's a typo on the phone.
I'm not sure what you...
Go back and said 10%.
I think right there.
Yeah, I think this is it. So
Go forward.
So here it is. The comparison between 10 and 21%.
So I think on another slide, you have the values.
No, I have no values for this.
Keep going forward.
Right here.
So on the O2 TGA, it's 0.01. Was that 1% or 10%?
And no, it's based on the sample in the FTC user guide of the example of the FTC user guide. So it is it's not percent. So it's 0.01 and 23rd%. Yes, mass fraction oxygen.
Okay.
It's not the volume fraction.
Okay.
Okay, sure. One more question.
Were you able to verify the parameters you found with the one found in literature, or are they not available? Or
I
how do you compare them?
The results of the TGA experiments, I also compare them with the literature. So they're similar, but we have all a range in literature. So do you see also for the polyurethane, the third and fourth reaction wasn't typical because we take a flexible foam from supplier. So it was not only polyurethane. So it's very important to know which materials do you have, but also if you know it, you cannot be sure it's react like in the literature. So it's not only to take the information and the data from the literature. So it could be that you have a completely different fire behavior, especially for the simulation. And also PMMA and was the same like documented, described.
Okay, I think we really need to go on to the next speaker, but thank you very much.